This lecture is on fundamental concepts in fluid mechanics. Okay, let's talk about density, which is the first property in this lecture on fluid properties. So the density that can be shown using the Greek letter rho refers to the mass of the fluid that is contained in a unit of volume. And it can be measured in SI units of kilograms per meter cubed because it shows how much mass is contained in, for example, 1 cubic meter, and it is determined from this formula. Rho equals m divided by v, and v is shown like this, which is something like an upside down a, so that it is not confused by v that can be used as velocity. So rho equals m divided by v, in which m is the mass of the fluid and v is its volume. And this figure is also showing this cube has a mass m and volume v. So the density is mass divided by volume. A liquid is practically incompressible. So what does it mean in terms of density? It means that the density of a liquid varies little with pressure. So as pressure increases or decreases, the density of a liquid does not change much. However, it has a slight but greater variation with temperature, which means that temperature has a little bit more impact on density. For example, water at 4 degrees C has a density of 1000 kilograms per meter cubed, whereas at 100 degrees C, which is the boiling point of water, its volume will expand, and so rho of W, which is density of water, will be less, which is 958.1 kilograms per meter cubed. So if the temperature range is small, so this is the conclusion. If the temperature range is small, we can consider the density of a liquid to be constant, so its volume does not change, and therefore the fluid is referred to as incompressible. So again, if the temperature does not change much, then we can consider the fluid to be incompressible. So this is a question for you. What is special about the 4 degrees C water? So maybe you can do a research on this question. There's something special about water at 4 degrees C. All right. Let's see how gases work when temperature and pressure changes. So gas has a higher degree of compressibility, unlike liquids. So unlike a liquid, temperature and pressure can significantly affect the density of a gas. As an example, air has a density of rho equals 1.23 kilograms per meter cubed when the temperature is 15 degrees C. And the atmospheric pressure is 101.3 kilopascals, in which pascals is basically 1 Newton per meter squared. But at this same temperature and at twice the pressure, the density of air will double and become rho equals 2.46 kilograms per meter cubed. So you see how significantly a change in pressure can actually impact the density of a gas, in this case air. Next important property of fluids is specific weight. Let's see what it means. The specific weight that can be shown using the Greek letter gamma of a liquid or of a fluid is the weight per unit volume. So previous one, we had density in which was m divided by v, and m was the mass, but here we have weight per unit volume. And it is measured in newtons per meter cubed, as an example in SI units. And the formula for gamma is W divided by V, in which W is weight of the fluid. Again, in density, we had rho equals M divided by V, but for a specific weight, that is gamma, the formula is W divided by V, and W is the weight of the fluid. And you know that W is basically M times gravity. mg equals W. And this figure is also showing that this cube has weight W and the volume is V, so the specific weight is weight divided by volume. Since weight is related to mass by W equals mg, the specific weight is related to the density by gamma equals rho g. Next important property is specific gravity, and that is the ratio of a substance's density or a specific weight to that of some other substance that is taken as a standard. For example, as a standard, we can compare the density or a specific weight of other materials to water. Water at an atmospheric pressure of 101.3 kilopascals and a temperature of 4 degrees C is taken as the standard. The formula for a specific gravity is S equals rho divided by rho W, which is also equal to gamma divided by gamma W. And as I said, the standard is water at an atmospheric pressure and a temperature of 4 degrees C. And the density of water for this case is 1000 kilogram per meter cubed. So this is the answer to that question that was written in red in previous slides. At 4 degrees C, the density of water is maximum, and that is equal to 1000 kilograms per meter cubed. That is taken as the standard when we are calculating specific gravity. Example, if an oil has a density of rho sub O, which is density of oil, equals 880 kilograms per meter cubed, then its specific gravity will be S sub O equals 0.880. So, as you can see, it's unitless because it's a ratio and we're dividing row by row, so it's unitless. Another example, if 6 meters cubed of oil weighs 47 kilonewtons, calculates its specific weight, density, and specific gravity. Let's see how we can solve this question. So, we know that gamma, which is a specific weight, is W divided by V. If we plug in numbers here, since we know the weight is 47 kilonewtons and we know the volume, 6 meters cubed, we get gamma equals 7.83 kilonewtons per meter cubed. So this is the specific weight that we just found. Next, let's find density. So in order to find density, we know that from previous slides that gamma equals rho g. So if we rearrange those, we get rho equals gamma divided by g. Again, from previous slides, you should remember that gamma equals rho g. So if we rearrange that to get just rho equals gamma divided by g. And we already found gamma, so if we divide it by 9.81, which is the gravity, we get 798 kilograms per meter cubed. So this is the density of oil in this question. And then finally, we want to find a specific gravity. A specific gravity is rho divided by rho of water at 4 degrees C, So we already found rho, and we know rho of water at 4 degrees C, which is 1000 kilograms per meter cubed. So if we divide those, we should get a unitless number. In this case, it is equal to 0.8. Next important property of a fluid is bulk modulus. The bulk modulus is the measure of the amount by which a fluid offers a resistance to compression. So bulk modulus deals with compression, resistance to compression, how much we can compress a material. Again, it's a measure of the amount by which a fluid offers a resistance to compression. The formula for that is E sub V equals negative dP divided by dV over V, in which dP is the incremental pressure and it equals dF divided by A. So this is basically the definition of pressure, force over area. And in the denominator, we have dV over V, which basically shows decrease in volume per unit volume as a result of pressure applied on that object. And we have this negative sign here. The minus sign shows that the increase in pressure, that is positive, causes a decrease in volume, negative. So in order to get a positive number for bulk modulus, we need to have a negative sign here in this formula. And let's see what this figure is showing us. So there is a cube in which force is applied on all sides, and as a result you can see that the final volume is less than the original volume. Typical units for bulk modulus are Newton per meter squared or Pascal. For a liquid, because the density of a liquid changes very little with pressure, its bulk modulus is very high. Let's look at an example here. What is the percent of compression of water at the deepest region of the Pacific Ocean, where the water pressure is increased by 110 megapascals? And seawater at atmospheric pressure and room temperature has a bulk modulus of about 220 gigapascals. So we have to use the formula from previous slide, and if we rearrange that and just isolate the denominator in the previous formula that we had on the left side and other values on the right side, we get the change in pressure, which the question mentioned is 110 megapascals divided by bulk modulus. So what we are doing here, we are just rearranging the formula in the previous slide to get delta V over V and find out the percent change of compression of water at the deepest region of the Pacific Ocean. So delta V divided by V equals 110 times 10 to the 6th pascals, because it's mega, so it's 10 to the 6th, divided by 220 gigapascals. And giga is 10 to the 9th, so it's 2.2 times 10 to the 9th pascals. So the result is 0.05, or basically 5%. And for a gas, because of its low density, thousands of times more compressible than a liquid. So a gas is thousands of times more compressible than a liquid because of its low density. Therefore, its bulk modulus will be much smaller. So when bulk modulus is high, means that the resistance to compression is high. But when the bulk modulus is low, it means that resistance to compression is low, such as a gas. Another example, An amount of glycerin has a volume of 1 meter cubed when the pressure is 120 kilopascals. If the pressure is increased to 400 kilopascals, determine the change in volume of this cubic meter. The bulk modulus for glycerin is E sub V equals 4.52 gigapascals. All right, let's look at the solution. First, the pressure increase applied to the cubic meter of glycerin is delta P equals 400 kilopascals minus 120 kilopascals. That equals 280 kilopascals. So this is delta P. Because the question says the pressure was 120 and then the pressure increased to 400. So delta P is 400 kilopascals minus 120 kilopascals, which is 280 kilopascals. Therefore, the change in volume, we have to use that formula again, E sub V equals negative delta P divided by delta V over V. So if we plug in numbers here, we know that E sub V is 4.52 gigapascals, so it's 4.52 times 10 to the 9th newtons per meter squared. That equals negative delta P that we found here, 280 kilopascals, so 280 times 10 to the 3rd newtons per meter squared divided by delta V over V. And we know that the original V was 1 meter cubed. So by solving, we get delta V equals negative 61.9 times 10 to the negative 6 meter cubed. So this is how much the volume will change. Next topic is on ideal gas law. Let's see what it is. There are two conditions for a gas to be an ideal gas. First, to have enough separation between its molecules so that the molecules have no attraction to one another. So this is the first condition. And the second one, the gas must not be near the point of condensation into either a liquid or a solid state. The formula for ideal gas that relates density, temperature, and pressure is P equals rho times R times T, in which P is the absolute pressure, which is referenced from a perfect vacuum. Rho is the density of the gas. R is the gas constant. For example, for air, it is 286.9 joules per kilogram Kelvin. There are different values for gas constants, and this value is for air. And T is the absolute temperature in Kelvin. So T is in Kelvin. Example, air contained in the tank shown in this figure is under an absolute pressure of 60 kilopascals. Again, absolute pressure is relative to a perfect vacuum. Is under an absolute pressure of 60 kilopascals and has a temperature of 60 centigrades. Determine the mass of the air in the tank. And we know that for air, the constant is 286.9 joules per kilogram Kelvin. So first step, because the temperature was given in degrees C, we have to convert that into kelvins because the formula uses temperature in Kelvin. So T sub K, which is temperature in Kelvin, equals T sub C, which is temperature in centigrades, plus 273. So 60 plus 273 equals 333 kelvins. The formula was P equals rho RT. So if we plug in the numbers and rearrange, we get rho equals 0.628 kilograms per meter cubed. Now we found rho. In order to find mass, we know that rho is m divided by v. And from this figure, we know that the radius at this point on the side of this tank is 1.5. So the volume of this cylinder or this tank is A, which is area at this side, times 4 meters. So that is pi r squared times 4. So the denominator here gives us the volume of the tank. And then we know the rho, we calculated that as 0.628 kilograms per meter cubed. So we can find m. So m equals this number multiplied by this. So m equals 17.8 kilograms. And this is the final answer for this example. Next important property for fluids is viscosity. It's basically the property of a fluid that is used to measure the resistance to flow. The higher the viscosity, the more difficult it is to move through the fluid. Example, it is easier to move through air compared to water because it has a lower viscosity. It is less viscous. Let's watch this video. So on the left, we have a fluid such as water, and on the right, we have another liquid that was more viscous. And this one shows a very viscous fluid, and as you can see, it's very difficult to flow. Okay. But what causes viscosity? The physical cause of viscosity is the continuous motion of fluid molecules. So suppose that this is a pipe and some liquid such as water is flowing into it. So when a faster molecule from the top layer moves downward, it transfers momentum to slower molecules in the bottom layer, so pushing them along. And when a slower molecule from the bottom layer moves upward, it slows down faster molecules through momentum exchange. As a result, these interactions create resistance, leading to viscosity. Next, let's talk about Newton's law of viscosity. So, when a very small force F is applied to the plate shown in the figure, so there's fluid and then a plate on top of it. When a force F is applied to this plate, it will cause elements of the fluid to deform as shown in this figure. So they form something like a trapezoid. After a brief acceleration, the viscous resistance of the fluid will bring the plate into equilibrium. And the plate will begin to move with a constant velocity u. And because of the no slip condition at the bottom, because the friction is high and we have no slip condition at the very bottom, the fluid particles at the fixed surface remain at rest. So the fluid particles at the very bottom, they remain at rest. And those on the plate's bottom, which is here, they move with the same velocity as the plate, u. Okay, next Let's talk about shear stress. So this effect subjects each element of the fluid to force per unit area, to a force per unit area, or shear stress tau. And shear stress is produced by a tangential force delta F that acts on the top and bottom area delta A of the element. So we are analyzing one single element inside water in which the force is applied on it because of this movement. Because of the movement of the plate, we saw in previous slide that liquid elements will deform, and that's because of the force applied on them, and that force causes shear stress. And the formula for that is tau equals delta F divided by delta A, or dF divided by dA, when delta A approaches 0, which means that if you're analyzing a very, very small portion in which its area is very close to 0, then instead of delta F divided by delta A, we can say dF divided by dA. So this d means that that value is very, very small. And since the fluid will flow, the shear stress will cause each element to deform into the shape of a parallelogram. So this shear stress causes deformation in that element, and it will form something like a parallelogram. And during a short time delta t, the resulting deformation is defined by the shear strain specified by the small angle delta alpha, where delta alpha is approximately equal to tangent delta alpha, and that's equal delta x divided by delta y. This definition of tangent, this side divided by this side. And unlike a solid that would hold this angle under load, a fluid element will continue to deform. This is very important. So when you have a solid object and you apply shear stress on it, when you release the force, the object will go back into its original shape, something like this. But for a fluid, it's not the case. For a fluid, as long as you apply the force, it will continue to deform. So in fluid mechanics, the time rate of change in this shear strain or angle becomes important. Let's watch this video and see what it means. So as this plate starts moving, you can see how this element inside this fluid deforms. And on the edge here, we have no slip conditions, so no deformation. But as long as this plate rotates, we will have displacement or deformation of fluid elements inside here. Next important property of fluids is vapor pressure. So in a closed tank, such as the one in this picture, the liquid's temperature will cause continuous thermal agitation of its molecules. And as a result, some of the molecules near the surface leave the surface, which is evaporation. So they evaporate into the vacuum space of the tank, which is the space above the liquid inside the tank. And eventually a state of equilibrium will be reached after some point, after some time. So number of molecules that evaporate from the liquid, in that case, when equilibrium is reached, number of molecules that evaporate from the liquid will equal the number of molecules that condense back to it. So this is the state of equilibrium. And under that condition, the vacuum space is then said to be saturated. So the evaporated molecules create a pressure within the tank. So in this region, there will be some pressure because of the evaporated molecules that exist in this region. And that is called the vapor pressure that we can show with P sub V. Higher temperatures will cause higher vapor pressures. So one question here, why knowing the vapor pressure is important? What do you think the answer is? The reason is that the liquid will begin to boil when the absolute pressure at its surface is at or lower than its vapor pressure. Next, let's talk about a very important phenomenon called cavitation. So when designing pumps, turbines, or piping systems, the liquid at any point within the flow should not be subjected to a pressure equal to or less than its vapor pressure. Cavitation occurs when the pressure in a liquid drops below its vapor pressure, and it causes formation of vapor bubbles. And as these vapor bubbles that are formed in regions with lower pressure transfer to regions of higher pressure, they implode and they create a jet that is very destructive and causes surface erosion. Next slide, we have a video explaining how cavitation occurs.
Welcome to e-learning in thermodynamics and fluid dynamics of our bachelor program in renewable energies and environmental technology. In this series, we are going over the phenomenon of cavitation in water and its consequences. What is cavitation? Cavitation is the rapid formation and collapse of vapor bubbles within a liquid. Such cavitation bubbles are formed mainly in locations within the liquid where the static pressure becomes smaller than a liquid's vapor pressure. The phase diagram of water shows if water is in its gaseous, liquid, or solid state, depending on temperature and pressure. The horizontal axis of a diagram represents temperature, while its vertical axis shows pressure. The vapor pressure curve is part of a phase diagram. It indicates at which pressures and temperatures water evaporates from liquid to vapor or condenses from vapor to liquid. At a constant pressure of 1 bar absolute, water in its solid state, which is ice, melts to liquid water at a temperature of 0 degrees Celsius. Keeping the pressure constant at 1 bar absolute, liquid water evaporates when the temperature is increased above 100 degrees Celsius. Evaporation of water is not only possible when the temperature is increased at a constant pressure. The other possibility is to keep the temperature constant and reduce the pressure below the vapor pressure. Water can evaporate and condensate at temperatures below 100 degrees Celsius if a static pressure is low enough. This is exactly what happens when cavitation occurs. Bubbles of water vapor form when the pressure in a certain location decreases below the vapor pressure. The vapor condensates back to liquid once the bubble has reached a location with a pressure above the vapor pressure. But how is it possible that the pressure becomes very low in certain areas of a fluid? Let's have a look at an example for illustration. If objects, such as blades of a ship propeller, are moved through water, there is a higher pressure on the side facing the flow and a lower pressure on the opposite side. On other edges exposed to the flow, low pressure can also lead to cavitation. The bubbles collapse as soon as they reach an environment with a pressure above the vapor pressure. When pumps circulate water through piping systems, cavitation can occur where the pressure is lowest, at the inlet of pumps and in narrow pipe sections. If the pressure at the inlet of a pump is low and approaches the vapor pressure, cavitation can occur at the pump impeller as we have seen it at the ship propeller. The pump can deliver less water because the cavitation bubbles occupy a part of the cross-sections where the water should flow. Damage from collapsing vapor bubbles will be shown later. The same amount of water per time flows through the pipe with a large cross-section as through the narrow cross-section. Therefore, the velocity is higher in the narrow part and the static pressure is lower. The pressure is especially low at the exposed edge at the inflow side of a narrow part. We show a detail of a phase diagram of water, which allows to analyze the situation in a narrow pipe section. The temperature of a flowing water can be 20 degrees Celsius, which is a vertical line in the diagram. It crosses the vapor pressure line at an absolute pressure of 2,300 Pascal. As long as the pressure is higher, water remains liquid. If the absolute pressure decreases below 2,300 Pascal, water evaporates. The colors in the left visualization correspond to the colors indicated on the vertical axis of a phase diagram on the right. Upstream of a restriction, the static pressure is well above the vapor pressure. The static pressure in the flow decreases as the flow reaches the narrow pipe section. In our example, the pressure at the exposed edge is below the vapor pressure. Consequently, water evaporates and cavitation bubbles are formed. The low pressure at the exposed edge causes cavitation bubbles to form. At a pressure of 2,300 Pascal, a certain mass of water vapor requires over 50,000 times more volume than in its liquid state. The bubbles collapse as soon as they reach a region with a pressure above the vapor pressure. Because water from the vapor bubble occupies 50,000 times less volume after having condensed to its liquid state, the collapse of each bubble is a spectacular event and emits pressure shocks. Pressure shocks from many collapses result in an audible noise very characteristic to cavitation. The sound used now in the video has been recorded in an experimental setup similar to the one in the animation. But how does it look like when cavitation bubbles are formed and collapse in detail? We can see the formation and the collapse of cavitation bubbles with a diameter of approximately 9 mm in slow motion. In real time, this process takes about 4 milliseconds and it is a spectacular physical event. Because liquid water occupies many thousand times less volume than vapor, the bubble implodes. It first assumes a ring shape. Shock waves and a strong microjet are the result of a collapse. Let's go through the whole process again. If the local pressure decreases below the vapor pressure, water evaporates. A cavitation bubble is forming, is growing larger, and is transported with the flow to a region with a higher pressure. The bubble stops growing. If a local pressure exceeds the vapor pressure, vapor condenses, starting from the bubble's wall. Its surface starts to break down at its weakest spot. A microjet forms and pierces into the bubble's opposite surface. The bubble is now collapsing. The bubble becomes a torus and disintegrates further. The microjet continues to flow in the liquid and can hit a wall. Through its concentrated impact, even high-strength material can be damaged. The implosion releases energy in a very short time concentrated in a very small spot. If the microjet hits a surface, it damages the material by a localized short-term overstraining. The material starts to evolve microcracks, and later material can break off. We show a few examples of damage in pump impellers kindly provided by the Swiss pump manufacturer Herney. A brand new impeller to the left in comparison with an impeller having been continuously exposed to cavitation during 6 months, another impeller with damage from 12 months operation in cavitation, and one from 24 months. The new impeller shows the geometry as it should be under normal operation without cavitation. After 6 months of operation under cavitation, material has been eroded in the center of the wheel. The respective areas are highlighted with grey color. The impeller blades are undamaged. After a year of operation under cavitation, the damaged geometry has a different shape, and therefore the flow has a different pattern. The collapsing cavitation bubbles cause material break-off at the top edge of the blades. After 2 years, the blades have been eroded completely, which makes it impossible for the pump to function. In this video, we have shown the basic mechanism leading to the formation of cavitation bubbles, which reduce the flow of water. We have also seen the spectacular collapse of cavitation bubbles, leading to noise and damage even to high-strength material. Systems have to be designed such that cavitation is avoided.
Let's watch another video.
Before designers can build a quiet propeller, they have to understand why it makes so much noise. If a propeller spins quickly, it leaves a trail of bubbles behind it. As the bubbles pop, they make a lot of noise. These bubbles are not filled with air, but with steam. The steam is produced by the seawater boiling.
It is a well-known fact that water boils at 100 degrees centigrade. However, few people will know that at different pressures, the water will boil at different temperatures. If you increase the pressure, as in a pressure cooker for instance, then the boiling point of the water increases. Hence, the cooking is more efficient. Few people will know, however, that at reduced pressures, water will boil at lower temperatures. I have here a vacuum pump, and I'm going to turn on the vacuum. This flask here contains water, and we have it connected to a pressure gauge, and we're reading at the moment approximately 15 pounds per square inch, which is 1 atmosphere. I turn on the pump, you notice the pressure dropping immediately, and as the pressure drops, as we approach zero, bubbles start to form, and the water starts to boil. So here we are at room temperature, but at a significantly reduced pressure, almost a complete vacuum, the water is now boiling. Water boiling at 20 degrees centigrade at almost 0 pounds per square inch, a remarkable phenomenon, sir.
When a submarine's propeller turns quickly, an area of low pressure is created on the blades. This lowering of pressure causes the water to boil without heating up and produces bubbles of steam. This is called cavitation.
Alright, next let's talk about surface tension and capillarity. But first we need to define two important terminologies, cohesion and adhesion. So this cartoon here shows cohesion and adhesion, but let's find out what they are. So, cohesion is responsible for maintaining a liquid in its form, and it's basically the attraction between the molecules of the fluid inside the fluid, and adhesion is the attraction between the molecules of the fluid and other kind of substances, such as the surface of the container. So a liquid maintains its form because its molecules are attracted to one another, and that is the definition of cohesion. And regarding adhesion, liquid molecules can also be attracted to those of a different substance, such as the liquid's container, and that is the definition of adhesion. Let's find out what surface tension is and what causes it. So here in this figure, we have one molecule that is inside the water and another one very close to the surface. So with this one, at some depth inside water, that molecule is surrounded by other molecules, so there is attraction between them. As you can see, the resultant force here, the resultant cohesive force is 0. Because we have, for example, this vector here and this vector here that cancel out, and the same applies to other ones. But there is another molecule here that is on the surface, and as you can see, there's attraction between this molecule of water and other water molecules. And as you can see, the resultant force here is downward. The resultant force here is downward because these vectors do not exist on the top. So the resultant force is downward. Resultant cohesive force is vertically downward for any molecule that is on the surface. So, since there are molecules on the surface that are attracted to one another, it produces a contraction of the surface. And that is similar to when molecules tend to restore a stretched elastic film, and that is called surface tension. And that is shown with letter sigma. And it is measured as a force per unit length in any direction along the surface. And sample units for surface tension, or sigma, is newtons per meter. And that is the reason that, for example, an insect, as shown in this figure, can basically stay in water or walk on water. That's because of surface tension. That is basically this attraction between the molecules on the surface. Sigma for any liquid depends on the temperature. So as the temperature rises, surface tension goes down, and this is what this figure is showing. So different colors here are for different liquids, and as you can see, as temperature rises, surface tension goes down. And the reason, it is due to the thermal agitation of the liquid's molecules. As an example, water at 10 degrees C has surface tension sigma equals 74.2 millinewtons per meter, but water at 50 degrees C has sigma equal 67.9 millinewtons per meter. Also, values of sigma are very sensitive to impurities. Capillarity is the phenomenon where liquid rises or falls in a narrow tube due to the combined effects of cohesion, adhesion, and surface tension. And the capillarity of a liquid depends on the comparison between the forces of adhesion and cohesion. But let's find out how. If the force of a liquid's adhesion to the molecules on the surface of its container is greater than the force of cohesion between the liquid's molecules, then the liquid is a wetting liquid, such as water. That the surface of the liquid will be concave. such as in this case shown in this figure. And if the adhesive force is less than the cohesive force, then the liquid is a non-wetting liquid, and the surface of the liquid will be convex, such as the case for mercury, and it is shown in this figure. So as mentioned in the previous slide, we have wetting and non-wetting liquids. So the difference between them is that wetting liquids will rise up along a narrow tube, such as the case shown here, that this container is filled with water and then there is a narrow tube. So water will start rising in that tube. So that is a wetting liquid. And the free surface makes a contact angle theta with the sides of the tube. And if the fluid used is water, usually that contact angle is 0. So if we analyze the forces in this portion of the tube in order to find how much water or that liquid rises in the tube, we have sigma Fy equals 0. And based on the analysis, we can have this formula for H, that H equals 2 sigma times cosine theta divided by rho gr. As an example, for a 3 mm diameter tube containing water at 20 degrees C, where sigma is equal to 72.7 millinewtons per meter and rho equals 998.3 kilograms per meter cubed, we can find H, which is how much water will rise in that tube, which is 3 millimeters in diameter. So if we plug in the numbers, and as I mentioned earlier, the contact angle for water is about 0 degrees. So in that formula, if we put 0 for theta and calculate this fraction, we get 9.9 millimeters. So this is how much water will rise in that 3 millimeter diameter tube. Another question, water at 25 degrees C is contained in a narrow vertical tube with a diameter of 4 millimeters in this case. The surface tension of water at this temperature is sigma equals 71.97 millinewtons per meter, and its density is rho equal to 997 kilogram per meter cubed. Number 1, determine the height h to which the water will rise due to capillary action if the contact angle theta is 0. And number 2, what will be the capillary rise if the diameter of the tube is reduced to 2 millimeters? So at this point, you can pause the video and using the formula in the previous slide to find the answer. So the answers are, for number 1, H equals 7.36 millimeters, where we had that tube with a diameter of 4 millimeters. And in number 2, we had what will happen or how much will water rise if the diameter is reduced to 2 millimeters from 4 millimeters. So the H will double and that will become 14.72 millimeters.